good. Alright, these are your objectives. Alright, we can come back to those. To start with, what is red?
According to the data.
Oh, look, there's two. There's page 3 that tells you it's, what is it, 700? Which one are you looking at? Or are you looking at the colour wheel on page 15, which is more detailed? The colour wheel's much better. The spectrum's good for, I don't know, for something. But for today's lesson, probably 15's much better because it's broken up better. So you can see it's 647 to 700 nanometers. That's the wavelength. That's how long it is between crests. All right?
700
or
to
troughs.
647.
Yeah, so that's red. Is that red?
No. Yes.
If you see that, do you know it's red? Is there any other possible way to see that? For it not to be that and still see red?
Oh, like for example, yeah, probably.
For example,
When it looks like green, you can see it's red. You can see I don't know.
Yeah,
exactly.
Like colorblind people.
That's a good one. Yes, colorblind. So what's a colorblind person? Is it going to be red to them? Is that going to be the wavelength of red?
I think
It depends.
but I think
what
it depends on
colorblind
what color you can't see. Like they receive the wavelength of red, but then they see it as something else.
Okay.
Yeah.
And this are exactly the same. This has 1% chromium, which is a transition metal, by the way, of course. This one here has only 1% chromium as well, but it's green this time. It's green. It's the same thing, 1%. They both got 1% chromium ions. This one's a nice pink color. This one's a nice green color. Ooh. This one's a nice green color. Explain that. All right. Magic.
Oh, they have different chemical structures, so they attract different ligands. So they require different energy to get to the excited state.
Have you done your research?
Yeah.
Did you read the textbook?
I read the PowerPoint slides.
Yeah, there are 3 cones, okay?
Yeah.
So, it's not as easy as that. Not only are there 3 different cones, there are overlaps. So red is not a color, it's a range. Alright? It's a range from 700 to here. It peaks out at here. So anything in this sort of level here, you'll think is red. Alright? That one's green, that one's blue. It gets worse. There aren't many of these blue ones. So you can't see blue very well. And there are lots of these red ones. So flowers have worked this out, that mammals, birds and humans have a heck of a lot of these red ones. And so if they're looking for that sort of person to pollinate their flowers, they make sure their flowers are red. Whereas insects are good on the IV level, so if you in ultraviolet UV level, so their flowers are blue.
Yeah.
So it's a perception of your brain of where the wavelength is and how well it can read, and then your brain interprets that as a color. Okay? So, is it red? What is red here? So that's sort of the blue and the red. So it's absorbing the blue and the red, and it's exciting that energy up, and as it goes back down, it's releasing it in this sort of green area. So funny enough, it looks green. Okay? And it just so happens that this area here you can see, that's where you see the greens, right? That registers on the greens. Alright, same with the reds. It just so happens that you're absorbing certain wavelengths and releasing it. You're releasing quite a lot of blue here, and you're releasing an equal amount, really, it's not that much difference, of red. So why is it red and not blue? Is this really red? Besides the fact it's pink. So why is it pink?
You see.
Look at this. I think that's fair enough. This should be blue, shouldn't it?
No, this is a lot of red.
They're more red.
Yeah.
Okay, there's a lot of red, but what else? Look at these.
You look.
Massive number of red cones. You've hardly got any blue cones at all. So, is it really pink?
No.
It's not. I don't think it's pink. Alright, so can you really say this is red?
Crap, no.
You have no idea if that's red.
Oh my god.
You have no idea.
T-okay.
So you seriously have no idea if that's red.
Yeah.
Alright? It could be this. It could actually be half blue, half red. You
What
don't
is it?
know.
Wait, this is purple.
Your brain, as far as the numbers and the scattering of your cones are concerned, obviously it's red. Alright, now I think that's a nice red. There's biological variation in this room. You may not think that's a nice red, and it could be because you've got slightly different cones. All right, and for some of you it may be black if you're really extreme and got color blindness. But there are degrees of color blindness. So is it red?
We don't know.
I don't really know.
Oh God.
If there's an exam, what do you say?
It's a rain.
It's red.
Oh, what? Oh.
It's red. Let's do this one, okay? If green is absorbed, will you see red? Yes or no? Where's it gone?
Yes.
Can't see it. I've got buttons and stuff all over the place. Alright, let's get rid of the green. I've got lag on here. Is it going to go red? It goes purple. Are we happy with that? Near enough. Okay, there's green. I can put a line over here, across there, on the borderline. Alright, what else do we have? If we absorb violet, if the thing absorbs violet so there's no violet, are you going to see yellow? Yes or no?
Yes.
I don't think so. What did I say? Absorb red?
Violet.
Yeah, but how do you make violet? You go.
We're meant to see yellow. If all the red's absorbed, we get yellow.
Oh, wait.
We got a light blue.
It's blue and violet.
What did I say? Absorb violet. How do you get rid of violet? Who's good on their color wheel?
Blue and red.
I need to go to a color wheel now. Violet is what? Blue and red.
Yeah.
Oh, so I get rid of this one. Of course, it's going to
Oh,
go
God.
green. God. All right, there we go. Surprise, surprise, it's green. So the color wheel works. Okay. Why does it work? God, that's too hard a question. That's what we've been talking about today. Okay. You won't get asked that. All right. It's too hard. So, what do you have to know? You have to know on page 13. You look here. And if you see yellow, go backwards. That's the color that's being absorbed. If you see orange, blue is being absorbed. If you see red, you get it? Get my picture?
Yeah.
That's how the color wheel works. The reason we get colors is because the d-orbitals split. So, what's happening? These are two different chemicals. This has been split in two different ways. So let me just forget about one of them. All right, maybe this one because it's clearer. All right. So you can see here that. I prefer this one actually. Alright, these ones here are longer. This is probably more realistic of what it really looks like before anything's happened. Alright, it's obviously way over exaggerated. These ones here are the DZX. Okay? Can you see how there's a little band, a little round thing here? The idea is intuitively that that's putting pressure on here, so the lobe here could be longer, all right? And because this little thing's here, anything that's on this XY plane, which is most definitely not this one, definitely not this one, and this one is, but so is this one too. And for some reason, this x squared, y squared gets pushed out by these inner circle, and this one doesn't get pushed out by the inner circle. Alright, so what you have is a splitting here. So you get these guys here seem to get pushed out further on the outside than these ones here, these three. So these simple ones, dxy, dyz, dxz, are slightly closer than the other ones, so electrons can pop back and forth here. Alright, and it just so happens that's the perfect distance to create color. Yeah? Which is rather trivial, isn't it? Alright, because do you think that's the only thing an atom's doing? Electrons are going from here back and forth? They're doing all sorts of things. But your eyes are very, very limited and can only detect color, so we are fantastic about knowing all about this because we can detect color. I'm sure if we were insects, we wouldn't know, we'd possibly not even know this, all right, and we'd know all about something else that's really weird that's happening on inside the atoms. That just so happens to be the wavelength for X-ray, for UV. All right, so I heard another thing saying that it's quite remarkable human beings have developed good at light because light wavelengths, matter interacts with light wavelengths more than anything else.
So basically there's like axes, so the axes and electrons at the end of the axes. That's the electrons of the metal, like the one in the middle. And then the other one, that's a ligand. And then the lobes,
Keep talking.
basically the lobes, that's like the ligand. So then the d-orbitals, in the orbitals there's electrons, and then electrons and electrons they repel. So then if the lobes, for example, the x square y square one, the lobes are on the axes, and they're both electrons. So then they repel. So then it pushes the lobe off of the axis, causing the splitting because it wants to
Repel.
yeah, it wants to repel.
further.
So then, for example, if my arm is the axis, the x-axis, y-axis, or z-axis, and then there's this big meat thing on my arm, that would be the lobe. So then the meat thing is trying to get rid of my arm to get to another plane or another area. So it tries to leave, and then when it leaves, the energy release will be the wavelength that turns into the light.
Good.
Or the colors.
Yes.
And, for example, XY, YZ, and XZ, they're not overlapping on the axes. They're in the middle. So then they're like, for example, the furthest distance apart from the axes. And then that means that the repulsion is least. So that's why it's in the lower energy level than when it overlaps with the axes.
All right. So Alpha's just said everything before I got to the slides. I don't know if you understand that or not. Is that clear?
Yeah.
We'll go again. Now it's my turn. Alpha got the first shot at it. All right. Let me have a second shot at it. So I can't find anything on the internet that looks good. That's when I draw a picture. God, I haven't done that. I've probably done that 5 times in my entire teaching career of 10 years. I drew this picture. All right. Google doesn't have a picture that's good enough as far as I'm concerned. All right. So what happens is you will have ligands. All right. We're aware of the ligands already. All right. I'm going to jump down to your data booklet again. All right. I'll get to what Alpha was saying a bit later. Just let me get there a bit slower than him. Just jump to it. Have a look at this. Find it. All right. Where is it? You need to know it's there, and you need to go and just have a look at it. So hopefully you don't forget to go there when the test comes. You think, oh my God, how do I do this? You look up your data booklet. It's page 14. Can you see it? Everything's here on page 14 to 15. If you're here, that's everything for this unit. There's 3 things on there we need. All right. These things have different abilities to push electrons. Alpha was talking about pushing electrons. Let me go to the charge density areas. Where are we? Here. Oh, there. All right. If you see here, depending on the shape and structure of the molecule, which we're going to do in detail next unit, this one here is nonpolar. There's kind of no charge here. It's kind of neutral. This one has got extreme poles here. This is probably the next strongest one, and this one's probably the weakest one. Okay? So if this one would be negative, and that'd be positive. Oh, sorry. That's positive, that's negative. So that's negative, positive, negative, positive. So this is doing the dative bonding, the covalent dative bonding. This one here will have the better ability to put pressure on the electrons of these lobes. Would you agree? All right, because there's a high concentration. Look at your data booklet and see if that agrees. Look up ammonia and look up water, because I don't think these two are on there. All right, and see, is ammonia a stronger ligand than the water? And memorize that word charge density, because that's why. All right, there's a concentration of charge. Is it or not stronger? Is ammonia stronger than water? Look at your data booklet, it's right here. I'm showing the video, I'm not showing you. Can you see it?
Yep.
Can you see it? I'll protect you, I'll call you other names. Amy, can you see it? Amy?
Yeah.
You can see it? Good. Alright, Bill, can you see it?
I'm not gonna forget. But yeah.
Alright,
Oh God.
Yeah.
Sexy.
I'm just protecting you.
Yeah.
Are you posting us on YouTube?
Yeah, probably.
Okay.
Probably not, actually. It might be too crappy a video. See,
Dislikes.
I've got to cut out all this
10
rubbish.
dislikes.
That's all. I've got to cut. There's too much cutting. I don't have time. I'm too busy. All right. So remember this: the strength of the ligands based on the charge density. That's going to be able to push the electrons. Okay. So let's go back up to here. This here. So these electrons here, it's attracted to this positive nucleus. So when it comes down, it puts pressure on this electron. It thinks, hang on, I'm not comfortable being here. I'm getting squished here. I don't like this negative. I'm negative. I don't like this negative. I don't like you either. I'm just here because I've got the positive here. That's why I'm joining to you. All right, and so it quite happily pops off to one of the other lobes. All right, that's not under so much pressure from a ligand. Does that make sense? All right, so you have colors from transition metals already. All right, there are empty orbitals and they're jumping back and forth. But when you add ligands, you're changing these orbitals so that they're different distances. That's why you get the different colors, because now you're changing distances, so you're changing colors. All right, remember we did all those, we got four or five colors yesterday or the day before just from manganese. That's because you were adding different ligands, and the ligands were pushing down with different strengths, making this different. All right, can you see these two? Let's pretend these are both manganese. All right, you tell me which one has ammonia joined to it and which one has water joined to it. I'll give you two options. This is an extreme example, but can you tell me which one has water pushing on it? And tell me which one has ammonia pushing on it, and tell me why.
The blue one, that one.
This one has got what pushing on it? Which one's the stronger ligand? Ammonia. So which one's going to push down on the non-dxy, dyz, dz, x, whatever one? The one that's dx squared minus y squared or whatever, the complicated one. Ammonia is pushing down more on it. So is it going to be shorter or longer?
Shorter.
So is it this one or this one?
The red one. Wait,
Point to it, please.
Which one's manganese again?
This one's got the up-down, so this is the D with the funny little donut in the middle, and then this one here is the other one. So these are the extended, longer ones. So the ligands come and they put pressure on these ones first because they're further away. All right. So which one's going to get this? Is this going to be? This is the one that's squished more. So is it going to be? Is this going to have the ammonia or have the water? Ammonia. You got it, right? So this is manganese. This is manganese with ammonia pushing on it. This is manganese with water pushing on it. And when the electrons go from here to here, they'll be one color. But when they go from here to here, it's a different distance. So they'll be a different color. So you get the same chemical giving you different colors because you've got different ligands pushing on the d-orbitals, splitting them at different lengths. So there is overlapping orbitals between the ligand and this. They come and they overlap and put pressure. Okay? So this has caused electrons to move to the split lower energy levels. Alright, the movements between these energy levels causes the colors. So I've done this already. I think I'll just I'll skip that and go back to it. Shall I skip that and go back to it? Alright, this is the splitting. Alright, now the splitting is extremely confusing because there are these words that are extremely confusing. Alright, let's just try and do one by one. This one is called spin free because there are electrons here that are spinning free and not paired up. In this particular instance, the electrons have been pushed down off those onto the less energy ones, less energy lobes, and you can see that they are spin paired. Even though there's a free spin one there, the splitting is spin paired because it could go up to here. There's space for free spinning. Okay, that's difficult terminology. This one here is low spin because it's a low spin energy. This one's got a high spin, so it's more energetic here. And this one has had a very strong ligand putting pressure on it So there's a lot of energy being put into the system to push them out to these lower lobes. Okay? This is a maximum of 4. This is a maximum of 6. So the most you can have here, and it's in this order, I just want you to recognize this. Alright, so this can be 6, and this can be 4. This one's got 2 here, so you need to recognize that as electrons haven't been pushed down to the other lobes. Alright, so that's a free pair, a low energy split. Okay? High energy spin.
Stronger.
Kelly. Is cyanide stronger or weaker than water? Very good, stronger. It's pushed the electrons down here. And look what it's done to manganese. It's made it repelled by a magnet. It's changed its physical properties. That's pretty full on, isn't it? Just add a chemical to it and its physical properties have changed. And look at this one. If it's too weak, it has free electrons in free spins. It's now attracted to a magnet. That delta zero there, you need to know that, all right? Crystal field splitting energy, all right? Crystal field splitting energy is obviously influenced by the strength of the ligand, because that's what we've talked about all lesson. What else is it influenced by? As you go down a group, well, the PowerPoint tells you, the splitting increases, all right? Why is that?
They're at a higher energy level.
Yeah, it's wider, so it's easier. So the thing's attracted to the nucleus. It's gonna, because they're further out, they're gonna overlap more. The third one, somewhere, the oxidation state. All right, the higher the oxidation state of the cation, the more energy field splitting increases due to greater attraction of the nucleus to the ligand and hence more overlap. That makes sense, doesn't it? Make the thing more positive. You're going to get the ligand to attract even more. So there's going to be even more splitting. Last question. Here. All right. Look at that and explain to me which ligand is stronger and how you know it's stronger.
Oh, the down one.
The further you go down, the stronger the ligand?
Yeah.
Why do you say that?
Because it absorbs violet, which has a higher frequency and higher energy, I think.
Good. All right. So if you see yellow, then you look at your color wheel and you see violet, and that's got more energy than if you see green, because green's actually absorbing just red. Okay? So that's absorbed more energy. So this ligand, let's just do water and chlorine because that's hard to differentiate. All right. So the water has pushed these levels further apart so that it can absorb more energy. Is that fair enough? Yeah. Am I right or not? Can you check chlorine? Where is it? Yeah, it's there, right? Water is greater than chlorine. Are we happy with that?
Yeah.
I think that's about as hard a question as you could get asked. That's fairly tricky. All right, red is of lower energy, so the splitting must be less. All right, this one is higher, a longer distance, so the splitting must be more in order to have absorbed and released that energy.